Hello, this is Chloe Liebenthal. Welcome to my tutorial on using Nestpy to create standard plots. This tutorial is in the form of a Jupyter notebook, which you can access through a binder. Specifically, the tutorial is going to focus on using Nestpy to plot nests predictions and use them to analyze data. It'll introduce you to the basics of plotting nest curves, as well as some more advanced data utility functions that allow you to select datasets and compare and analyze them. Nest stands for Noble Element Simulation Technique. It's a C++ package that allows users to simulate various processes in noble elements such as scintillation, ionization, and electroluminescence. Modeling these processes is really useful for various fields of particle physics research, and it's particularly useful for low-energy nuclear recoils, such as the ones we'd expect from dark matter interactions, so it's a very useful tool for the search for dark matter. Right now, NEST is able to model these various processes in all three phases of xenon, solid, liquid, and gas, and other noble elements, such as argon, are also included in the model. Another key feature of NEST is that it allows users to change the parameters and details of the detector used in creating NEST's predictions. By using information about a pre-existing detector or creating a custom one, users can take variables like temperature, pressure, efficiency, and electric field variations into account for their predictions. Now, Nest's predictions are helpful because they're a really good supplement for experimental data. These predictions can help you to try and figure out what an experiment's results might look like before the experiment takes place. This can be really useful for formulating hypotheses and getting a general idea of how it might turn out. Then after an experiment takes place, comparing the data to Nest's predictions can indicate which data might be anomalous compared to the predictions. That can prompt researchers to take another look at that data and see what's going on there. Now, although Nest is specifically a C++ package, Nestpy is a complete Python binding for the Nest library, so it can be accessed through Python instead of C++. Simply importing the Nestpy module gives you complete access to Nest simulations. Now, the first part of our tutorial is going to focus specifically on plotting yield predictions. Using some of Nestpy's simplest functions, we're going to be able to plot the relationship between the recoil energy and the charge and light yields that are present during a nuclear recoil event. Recoil energy refers to the energy level of the collision when an outside particle hits a xenon particle inside a detector. Charge and light yields respectively refer to the amount of electrons and photons that are released by the collision. Our plots are going to include both charge and light yields. To start, we're going to need to import a few Python modules. In addition to Nestpy, NumPy is necessary for the mathematical functions we're going to use to generate our Nestpy predictions. Matplotlib is going to be used to create the plots themselves. Next, we need to start setting up the background information for the predictions we'll create. For this example, we're going to load up the pre-existing detector settings for Xenon 10. Then we're going to define the NC variable that stands for Nest calculations. It's the specific parameters of the calculations that Nest makes based on our detector settings. This way, calling NC later on will tell our Nestpy functions what these parameters are. Next, it's time to write the function that's going to calculate yield predictions. These functions, and there's going to be a couple of them, they use an array, which is a format NumPy uses to store data, and it's going to contain the various possible yield values based on different energy levels. Now, right at the start, we use np.vectorize we use that to make sure everything's going to be outputted properly as an array, and then we go on to write the functions themselves. Now, getYields vectorized is the function that generates our array of possible yield values. It does this by calling the built-in nc.getYields function, which is from Nestpy. However, nc.getYields needs something called keyword arguments. So what keyword arguments are the various factors that Nest uses to build its prediction. In this case, they include the interaction type. For this video, all of our predictions are going to be for nuclear recoil interactions, but Nest can also model other types of interactions. The keyword arguments also include the recoil energy value to base the yield prediction on, and the drift field strength. So, because we need these keyword arguments for nc.getYields, we have another set of functions. Those are photon yield and electron yield. Each of them calls getYields vectorized with different keyword arguments based on the yield type, charge or light. So this generates yields for either electrons or photons. Our next function is going to use the yields generated by getYields vectorized to output a tuple. This is a Python term for a sequence of other objects that contains Nest's predictions for recoil energy values and their corresponding yields. We're going to use these as the x-axis and the y-axis on our plot respectively. In order to generate these predictions, the function will use the functions we just wrote in our previous cell. Now, there's two inputs that are necessary for the nest curve function. The first one is field. That's the strength of the electric field in the hypothetical detector that Nest is imagining to make its predictions from. This is measured in volts per centimeter. The second input is yield type. This specifies whether the predictions are about electron yields or photon yields. Charge and light are the two inputs that this function can take for yield type. The nest curve function will first create a large array with a wide range of possible recoil energy values, specifically 1,000 of them. Then for each value in this energies array of 1,000 energies, the function is going to call the getYields vectorized function, using either electron yield or photon yield, depending on yield type, and it's going to predict what the yield would be at that energy level in the given field. NestCurve then returns a tuple containing the hypothetical energy values for the x-axis of our plot, and then the corresponding yields, which will go on the y-axis. Now that the functions to create nest predictions have been written, we can put them all together into a function that uses their output to create plots. Since it's helpful for a plot to include what versions of Nest and Nestpy were used to create it, we'll begin by creating a text box that contains this information. Next, we're going to write a function that uses matplotlib.pyplot, which we imported right at the beginning, to turn the values generated by NestCurve into a plot. As input, the yields plot function is going to need a list of different field values to generate its predictions for, as well as the yield type, which again can either be charge or light. There's also an option for the user to save their plot as a PNG image. By default, that's not going to happen, but it's a useful little function to have. Then the plot itself can be created. So let's take a look at exactly what's going on, because this is a pretty big function. First, as you can see, we define our version text box and the text box that's going to have the information in it. Then yields plot itself. First, the plot itself is created, and then a subplot is defined, which is how matplotlib stores information about our yields plot. Then we're going to give it a title. It's going to be either charge yields for nuclear recoils or light yields for nuclear recoils, based on what the yield type we input is. Each field then has a name generated for it to add to the plot's legend, which is going to show every electric field strength that the predictions are made for on the plot. Then the NestCurve function is going to create a full set of predictions, 1,000 of them like we said earlier, based on each field. All of these predictions are then going to be plotted. Then, based on whether the yield type is charge or light, the plot should be formatted somewhat differently in order to avoid text boxes and legends overlapping. Charge and light yields are also measured in different units. Charge yields are a number of electrons per kiloelectron volts, and light yields are a number of photons per kiloelectron volts, so the two plots also need different y-axis labels. The y-axis, which represents recoil energy measured in kiloelectron volts, also needs a label. We're going to set the x-axis to have a log scale, so it's going to depict the wide range of energy level as well. Then we just finish formatting everything by setting the margin to 0, so the plot's axes are not going to extend further than the data in the plot. This removes extra white space at the edges. Finally, if the user chooses to save their plot, we set file names for the PNG images. Now that that function's written, let's test out our functions. We're going to start by creating a light yield plot with just one electric field value to keep things simple. And it looks pretty great to me. So now we're going to move on and do the same thing, but for charge yield. They both came out really well in my opinion, so now we're going to try creating a charge yield plot and a light yield plot that have a wide range of field values that's going to generate a lot of predictions for us. As you can see, it takes a second, but look at that. That's a pretty wide range of various field values, all with their light yield predictions. Now we're going to do the same thing with charge yields. I think these look great, and if you actually go and visit the Nest website, these are the same plots that you're going to be able to see there. Now let's move to another type of plot you can create using Nestpy, a plot that compares Nest predictions to real data values. This plot uses many of the functions we wrote before, but it also incorporates real experimental data. First, we're going to need to import a few more modules. We import the JSON and glob modules because the data is stored in JSON format, and glob is useful for opening the files. Pandas allows us to use data frames, which is another kind of data format similar to a spreadsheet that's going to be used for opening our JSONs. And all of the relevant JSONs are stored in the binder in the charge and light folders, so you'll be able to follow along in the tutorial as well. We're going to open the data sets as pandas data frames. For this tutorial, I'm going to start by using one charge yield and one light yield nuclear recoil data set. Like I said, I have mine saved as JSONs as well as how they are in the tutorial binder, but on your own machine, you might have them stored differently. The getYields function is used to directly compare Nest's predictions to real data. It's similar to the Nest curve function, but instead of generating predictions based on a wide range of pre-generated recoil energy values, this function is going to take a list of energies as input and create yield predictions for each one. This is really useful for one aspect of the plot, the residual subplot, which shows how accurate Nest's predictions were. Now that we've written another Nest helper function, we can create another function using matplotlib.pyplot that generates a plot of our dataset and the Nest prediction curve, then a residual subplot that compares Nest's prediction to the real data to see how accurate the predictions are. So first of all, we create our plot, but this time around we're going to have two subplots to store information in, one for the main plot and one for the residuals. The one for the main plot is going to be a lot bigger. To create the experimental data on the plot, we need to pull the data out of the data frames we created earlier. The data frame also contains other useful information, like the name, the field strength, the yield type, and we're going to get some of that information as well. Then we title it. Again, that title is based on information about the yield type. Then, because not all data sets contain error information, we check if it exists, and we store error data only if it does. Then we're going to create the main scatter plot of the experimental data. This includes a bit of formatting such as color and a name label for the legend, which is a link to where the paper from the data is found online. If error information is included, we're going to add Y error bars to the scatter plot. Then we use the Nest curve function to create a curve at the same field value as the experimental data. We plot this in exactly the same way that we did in our last plot example. And we're also going to limit the range of the plot to a range of data values fairly close to those of the data, which just makes the plot a lot more readable. We add labels into legend, and then it's time to go create a subplot with residuals. That's a statistical method that compares the accuracy of a measured value and its corresponding prediction. Then we add some labels for the residual subplot and place a horizontal line at 0 to indicate the minimum amount of deviation from the prediction. If the residual value is sufficiently high, the subplot will change to a log scale on the y-axis, just so it's more readable. We're also going to add grid lines, again, readability, and then use the tight layout function, which improves the formatting all around. And now that we've defined this function, it's time to plot our data sets. Well, let's take a look at these. As you can see, we've got the actual data points represented by the dots, as well as the dashed line representing Nest's predictions. And we can use the residual subplot to compare using the sigmas for deviation. Just how different are the predictions and the data? In some cases, they're pretty close, but in some places, they're further off. Well, I'm definitely happy with how these plots came out, but it makes me wonder how Nest's prediction accuracy changes with field strength. So I'm going to use the functions I've written to go ahead and find out. First, I'm going to load all the data sets. This is what the glob module is really useful for. The plots are going to have field strength on the x-axis and percent error between the experimental data and the Nest prediction on the y-axis. The glob module is, like I said, what we're going to use to load up our files. So I'm going to quickly define a function called loadAll that converts the data in the JSONs to pandas data frames for every single JSON dataset that we've got in our binder. And now I'm just going to go ahead and actually create all those data frames. Next, I'm writing a getYieldDiffs function for yield differences. It reads each data frame, generates Nest's predictions for the recoil energy and field strength, and then calculates the percent error. Then the plotDiffs function is going to use getYieldDiffs to generate plots of the percent error versus the field strength. So as you can see, getYieldDiffs starts by reading out various relevant information from our data frame, and then it performs a percent error calculation on the experimental data and Nest predictions. It then returns a list of all these differences. Then there's the plotDiffs function. It plots the percent error as evaluated by getYieldDiffs. It takes a list of data frames as input, runs getYieldDiffs on all of them, and it outputs a plot that shows how different they are. So here is our plot for the chart for all of the charge yields that we have experimental data on, and it compares the charge yields to Nest predictions. As you can see, the further away from zero a dot is, the higher the percent error from Nest's predictions. Now, here's the same plot, but for light yields. With these plots complete, we can visualize Nest's general accuracy in predicting yields over a range of different field strengths. Notably, the percent error is a lot lower in around the 5 to 100 volts per centimeter range. That's actually because there's more experiments that use field strengths in this range, so that gives us more data to calibrate Nest with. Now that we've made these various types of standard plots, this tutorial is coming to a close, but there are still plenty of steps you can take to further your learning with Nest. Now that you know about the basic functionality, I hope you're going to use it some more and explore all its different utilities, of which there are a lot of really fantastic useful ones for lots of different particle physics experiments. And if you'd like to learn more about Nest, I'd recommend visiting the collaboration's website and GitHub page. You can find Nest publications, benchmark plots, citation information, and a lot of other really good info as well. Thank you so much for watching the tutorial.